After observing this is a constrained optimization problem, we should next try to write it down precisely. That is, we want to put it of the form max of area, but area is going to depend on some variables which we have yet to decide, and this will be supplied with a constraint which will also depend on the variables chosen. So the next task is to choose variables, particular ones that are convenient for which we can get an expression for area in terms of them, and perhaps also convenient in terms of giving us a constraint that's easy to deal with. So let's start by drawing a picture and deciding what variables we should choose. So let's give ourselves a circle, and on this circle we could draw an inscribed triangle. So let's say, without loss of generality, one of these points could be here. Then, this could be an arbitrary triangle, so another point, say, could be here, and another point, say, could be here. And so we can see an arbitrary triangle will look something like this. Okay. So our goal again was to find coordinates for the points on the triangle that will be convenient to us. So this one we've already fixed at r, 0. This one we could call x1, y1, and this point we could call x2, y2. So if this is a good coordinate system, then it should be easy to write down the area of the triangle in terms of x1, y1, x2, and y2. Now we have constraints in this case that x1 and y1 must be on the circle and x2, y2 must be on the circle. So here we have the constraint subject to x1 squared plus y1 squared equals r squared, and x2 squared plus y2 squared equals r squared. So the constraints are clear. But now we run into trouble when we try to find what is the area as a function of x1, y1, x2, and y2. The approach to do this may be kind of complicated. One thing we might think of is it's easy, or it's doable to compute, say, this length through the Euclidean formula for distance, and the same as this distance and that distance. And so we could express the lengths of each of the three sides of the triangle in terms of these variables, and then we could remember from trigonometry that there's this formula called Heron's theorem, which is a little bit complicated, which gives us the area of the triangle in terms of those lengths of the three sides. But what we're quickly seeing is that this is a mess. There's no convenient way to get a good area function in terms of x1, y1. And in this problem, we also have two constraints, which makes it more complicated. So let's scratch that idea and start again on a new, with a new idea. So let's give ourselves back a triangle. Instead of trying to write the coordinates as x1, y1, and x2, y2, why don't we try describing them in terms of the angle that they have. So this is angle 0, this is angle theta 1, and say this point as at angle theta 2. So then what we're trying to do is write the maximum of area of the function of theta 1 and theta 2 subject to a constraint, but in this case there is no constraint. Any theta 1 and theta 2 define a triangle that's inscribed on a circle. So if we want to solve this problem this way, we need a formula for area in terms of angle. And if we have that, then we could take the derivative with respect to both theta 1 and theta 2, set it equal to 0, and we'd be done. But in this case, we approach a similar problem that we had in the prior method, like knowing just the angles of these 3 points, one way of computing this area would be to try to compute the lengths of each of these sides of the triangles, and again use Heron's theorem, but this gets, like as before, kind of messy. So unless we can come up with a more convenient way to express the area of this triangle in terms of those variables, like we kind of have to scrap this approach. So in order to find a better system of variables to describe this triangle with, we might analyze first, why is this problem so complicated? And one of the reasons why this is complicated is because this is an arbitrary triangle. I mean, it could be a right triangle, it could be acute, or even obtuse. And so dealing with triangles in generality is somewhat complicated. So it's possible to ask ourselves, could we break this triangle into sub-triangles that are easier to deal with? And in this case, that is possible. We could see that since this is the origin, we could draw 3 sub-triangles by drawing these lines from the center of the circle to the edge of the circle. And now we have 3 isosceles triangles. And these, while isosceles triangle is not as convenient as a right triangle, it's at least much nicer than an arbitrary triangle. So now we may be able to guess that a good coordinate system is one where we have these interior angles, theta 1, theta 2, and theta 3. So the problem that we want to solve is we want to maximize area as a function of theta 1, theta 2, and theta 3, subject to a constraint. And in this case, it's clear what the constraint is. These angles, theta 1, theta 2, theta 3, must add up to 2 pi because they form the complete revolution. So here the constraint is that theta 1 plus theta 2 plus theta 3 equals 2 pi. So as before, we're golden if we can find a convenient formula for area in terms of these variables. But since our insight of this approach was to break the problem down into 3 simpler isosceles triangles, all we need to do is find out what is the area of an isosceles triangle of known angle. So let's give ourselves an isosceles triangle. And we could label this, say this is theta. And here in this figure we know that each of these sides is radius r. So here we would have an isosceles triangle with 2 sides of length r. And if we remember from trigonometry, the area of a triangle is the 1/2 the base times the height. So let's call this to be the base, and then the height is the perpendicular distance here. But that distance is precisely r sine theta. So then this triangle has area r squared sine theta. So now we can easily express area in terms of theta 1, theta 2, and theta 3. So we can write the problem as maximization of r squared sine theta 1 plus r squared sine theta 2 plus r squared sine theta 3, subject to the sum of the angles being 2 pi.